Thank you very much. Good day to all. Can you hear me? First question. That's great. All right. So, yeah, thanks for the introduction. I'm Marcin Rzez. I come from Poland, and yeah, I work for Iterators. We are a Scala-based, we are a Warsaw-based Scala consultancy company, and today I'm going to give a talk titled Idris For Practical / Impractical Scala Programmers. All right, thank you. So what Idris is, it's a kind of a research language, which is famous for its value-dependent type system. Scala, on the other hand, is, or maybe strives to be a practical language for solving, day-to-day problems. And it, at least at the first glance, at the surface, it doesn't have value-dependent typing. But what that actually is, what are the benefits of value-dependent typing? That's the thing I'm gonna talk about. This talk will roughly be divided into two parts. According to this slogan, I very strongly agree with. The first part will be theoretical. I will briefly talk about landscape. I'll try to sketch a landscape of type systems, of type system expressiveness, what that is, and maybe I'll try to explain what at least theoretically value-dependent typing is. Because, according to the slogan that's coined by Kurt Lewin, he was an American psychologist. I'm mentioning this because it's been attributed to a lot of people. There's nothing more practical than a good theory. Also, it's important to remember that you don't want to program in the most, or it's rarely the case where you want to program in the most expressive type system that's possible. Usually, the more expressive type system gets, the more guarantees you lose. For instance, type inference might be undecidable, or type checking times might be unbounded, meaning that your programs will never finish to compile. So it's all about finding a sweet spot, so to say, between how expressive type system is and how practical it is, I guess. And the other part will be where I show examples, where I try to transplant all these ideas into Scala, see if it's possible, and the cases where it works, the cases where it doesn't, and that kind of stuff. So to kick off the theoretical part, we have mainly two tools of exploring this type system landscapes. Well, there's more than two tools, but these are, so to say, main ones. One is the so-called lambda cube. It's a visual representation of type systems, and the other is called pure type systems theory or pure type systems framework. That's a definitional mathematical theory that describes type systems and the reasons about them. So lambda cube is basically this. It's a drawing of a cube, right? And the idea here is that when you traverse this cube in different directions, you form different type systems. You form them by kind of turning on and off various features depending on what directions you're traversing this cube. What these features that can be turned on or off are, well, basically these are the things that the type system can operate on, which are terms, and by saying that I mean things like constants, variables, expressions, recursively form of them, more and more complicated, when there were types, meaning expressions that describe type of expression form of terms. And so basically there are two things, and they can be mutually dependent. And so these are the dependencies that are that we can operate on, and you can turn them on and off. So you can have term, you can allow term to depend on term. You can allow term to depend on type, which is more or less parametric polymorphism. You can allow type to depend on term, which is a yeah, dependent typing, and type can depend on type, which is basically what you get is higher order types if you allow this feature. To give you an example of what I'm talking about, so when you allow only term to depend on term, that's what you get, basically, a lambda calculus. You can have constants, variables, functions, higher order functions possibly, and so on. Basically, the upper examples are in Scala, the lower are in Idris. So that's what you get. Computation-wise, it's very powerful. It's basically lambda calculus, but type-wise, you don't have much, as you can see. If you allow term to depend on type, then, as I said, you obtain parametric polymorphism. So here you have a term called identity. It's basically a function, and you allow it to depend on type, denoted by type variable a here, meaning you'll get a polymorphic function, right? If you allow type to depend on type, you can form this. You can form higher order types, basically. You can have things like a list type. So it's a type constructor which takes a type and forms another type, denoting list of the thing you passed here. And so on, so you can have functor type, function type, generically invariant, and so on, so on, so on. So this is what you get. You get higher order type, basically, if you allow this feature to be turned on in your type system. And that's where it gets interesting. If you allow type to depend on term, that's what this talk basically is in disguise. You obtain dependent typing. So for instance, here you have a poster child of dependent typing, a vector, which, as you would imagine, is a type constructor. It takes type and forms another type, but it also depends on a term, which is a natural number. 1, 2, 3, 4, and so on, so on. The idea behind this is that this natural number encodes the length of this vector. So the length of the vector becomes part of a type, which means the type checker can check various properties of this vector, like it checks whether you go incidentally off the vector or index of the vector, so it can check that. It's also possible in Scala, it might be a bit obscure, but here in the upper part, we have a term called depth as a function. It depends on another term, which is an argument of this function, but the return type of this function is dependent on whatever we pass in here. So if we set this, this type member v to, I don't know, int, this function will return int. If we set it to string, it will return string, and so on, so on. So that's how type on term dependency can look like. And yeah, the idea behind this cube is that if you go upward the cube, you add parametric polymorphism to your type system. If you travel to the back of the cube, you add higher order types, and if you travel to the right, you add dependent typing. Now, I will skip this part because we don't have that much time. If you're mathematically inclined, you can check the slides online. But the takeaway of this is that the theorem, the pure type systems theorem, or theory basically, can describe more type systems than can be found on the lambda cube. So there are type systems that are not to be found on this cube, on the corners of the cube, but can be derived from theory. But also, it's a point in the case where, which I made earlier, that you don't want to program in the most expressive type system possible. So, for instance, one of the type systems that can be derived from the theory is the infamous, I would say, system U. That's a type system where all types are inhabited. What that means and why is that the wrong thing? So, if you think of Curry-Howard isomorphism, which basically states that computer programs are equivalent to proofs. If I'm able to form a computation from A to B, then this means that I have proven that B holds under hypothesis of A, and the other way around as well. Then if all types are inhabited, then everything can be proven, which is obviously a wrong thing, a wrong property to have. If you think of it, if I give you a task of writing a function from A to B for any unrelated A and B, would you be able to do this? Well, yeah, no, because given some argument of type A, you can't, out of thin air, form an instance of unrelated type B. And if you think of it under Curry-Howard interpretation, that's a good thing, because that would, had you been able to prove it, that would have meant that if I know something, I know anything else. Which, well, your intuition tells you correctly, should be false, basically. But System U is very powerful. It has, for instance, a universal type constructor. It can create anything out of thin air. Thus, this is provable under System U. Which means that logical reasoning in this type system is totally meaningless. It's totally out of control, so to say. Well, there are other uninhibited types, like from A to A to A to A, which means that if you're given a function from A to A, can you derive A? Well, the only way you could possibly do it is to call function f on itself, but you would have then unbounded recursion, which means that this computation would never finish. So you can do this. That's sometimes equivalent to equivalent to bottom type. That's a representation of faults. So some types should remain uninhabited, but under System U, all types are inhabited, which means that it's totally, any reasoning in this type system is meaningless, basically. You don't want that type system. Let me show you examples of some basic type systems we have on the cube. So we start with some very basic one. It's in this corner of the cube. It's basically type lambda calculus. So the only dependency that's allowed is term-on-term dependency. As I said earlier, what you get computation-wise is lambda calculus. You can compute anything that can be computed in this system, but type-wise, you don't have that much. The only type you have is function type. And there is no polymorphism whatsoever in this type system. So basically, you are programming in lambda calculus, and no one in their right mind would like to program in lambda calculus. We need to have at least some real types, right, for type system to be practical. So we move to the back of the cube. We add type-to-type dependency to the type system, and thus we obtain type system called lambda omega. That's a somewhat strange type system where, because there is a type-to-type dependency or type-on-type dependency allowed, you can form elaborate types. You can have things like lists, either, and so on, so on. Also, you have everything you had in the previous type system, meaning lambda calculus. But because the only dependencies allowed in this type system are type-type and term-term, then this means that you cannot mix this word. Even though you can have arbitrarily complex types and arbitrarily complex computations, you cannot somehow mix these words, these two words. Which means that even though I can have a list of A's, I cannot write under this type system, I cannot write a generic function, say length, that would compute length of any list. What I can have is, because there is no term-level polymorphism in this type system, what I can write is a length for a list of ints, length for a list of strings, length for a list of, and so on, so on. Which means I'm basically, it's Go language level, and no one in their right mind would like to program in Go programming language, right? Which means that it's not really practical. We need to move on. We need to be able to mix these words for our type system to be practical. Words of types and words of terms. So we go up, and then we have a family of type systems, or two type systems. They are somewhat famous, the system F and system F omega. Why they are famous? Because, for instance, Hindley-Milner type system is a subset of system F. It's basically a subset for which type inference is decidable and has good time complexity. So once we're there, we basically have everything we are used to. Even more than that, because we have full power of lambda calculus at the type level, which means we can form arbitrarily complex types and mix them with arbitrarily complex computations. Well, if you think of it, if you have power of lambda calculus at type level, and lambda calculus can, in lambda calculus you can express computations that never finish, then you can have types that are so complex that type checker will never finish checking them. Which means that this type system is actually so powerful that the languages like Scala and Haskell, whose type systems are more or less based on this type system, deliver slightly less than this type system. For instance, one thing that's possible to express under system F omega is so-called higher rank polymorphism. For instance, it's not possible, it's not directly possible in Scala. What that means, let's take a look at this example. For instance, your intuition would tell you that this function, I'm not sure if you can see it. I take it as a yes. That this function should be compilable, right? So you take a function that forms tuples, and this, as you can see, this function has no type constraints whatsoever. It declares that it operates on any type. And so, yeah, your intuition tells you that if you pass an argument to this function, then you would have tuples of this argument of type B to this function, that you have tuples of B's. But this won't compile in Scala because Scala treats types A and B as unrelated types. So Scala type checkers will tell you that you're passing something that this function does not expect. What you would like it to have is to be able to quantify this type variable earlier at the level of the argument. You'd like it to be moved here, to be meaningful only here, and then it would work. It's possible, as in Idris' example, so where you can state that this type variable is meaningful only at the level of, or on the level of function argument. That's two-rank polymorphism because there is only one type parameter or type variable that you need to move, so to say, earlier in the process of quantification for it to work. You can work around this in Scala. You can use natural transformation or whatnot, but directly you cannot write it. It's possible under system F omega is not possible in Scala. So yeah, case proven, as Scala doesn't have all capabilities of system F omega. Well, you can do a lot. You can prove things like A and B implies A and B implies B on type level in Scala and Idris as well. But even though you have such a powerful type system that you need to limit a bit for it to be practical, still there are some deceivingly simple things that you cannot express in this system. For instance, collections of known length. That's the example we have seen earlier. Things like type of days where range of days is restricted according to the month, which is fact of life, that looks useful. But generically, you cannot do this under system F omega. Functions like sprint, that's an interesting case because at some level, sprint is a string-to-string function. But we all know that the argument to sprint function has internal structure. It's a format string. Depending on what you put in there, you obtain different types. For instance, S equals %D will yield a string to double to string function and so on, so on. But you cannot, and that's very useful. I mean, everyone uses something like sprint, but still, even in very expressive F omega type system, you cannot express it. So, we need to move to the right to solve these problems. And all these problems look, well, practical and useful. We would probably like, or you would probably like, to be able to state or check, or to have your type checker check the correctness of these cases. And that's dependent typing. That's what we want for these cases to be solved. And Scala does not intrinsically support it. The question is whether this additional type safety is worth the effort, whether it can be done, and, well, if so, what good does it bring? Right. So when I was researching this subject, I came across a Stack Overflow discussion where Miles said, or wrote actually, that there are some unique features of Scala, like singleton types, path-dependent types, and implicit values, that might make it possible for Scala to have good support for dependent typing. So let's try to see if this is the case, and in what cases it works, in what cases it doesn't, and more importantly, whether these features are enough to bring value-dependent typing to Scala. So, is it visible? Oh. Yes. All right, thank you. Okay, the left part is in Idris, the right part is in Scala. Okay, the very simplest the form of dependent typing is when type depends on enumerated dependency. Technically, it's dependent typing, as in type vehicle here, where it depends on a power source term, but this power source term can take only finite enumerated number of values, like here a petrol pedal or electric power source. Now, so this is the very simplest dependent typing form. Well, I would argue that this is what object-oriented is in disguise. And object-orientedness of Scala makes for a very good support for this kind of dependencies. You have numerous ways of encoding this kind of dependency in Scala. You can encode this dependency as subtypes, and all the constraints, like, say, refuel operation only works for petrol-based vehicles. They are naturally, they can be naturally written in this in Scala as in any other object-oriented language. You can do better than this. You can encode it as as mixin, as traits. If you think of it, it's even more expressive. This encoding is even more expressive than what you have on the left, because, for instance, if you would like to model hybrid vehicles, meaning the ones that are dependent on whose power source is either petrol or electric, then in Idris you would have to employ some advanced machinery, whereas in Scala it's very easy. You just mix into traits, right? And still, all the constraints, like refuel is only available on petrol-based vehicles, are easily obtained. You can be a bit more esoteric, you can code it as a phantom type, and so on, so on. So this kind of dependent typing is really well addressed in Scala. All right, can we do better than that? To have value-dependent typing, we need terms to be representable type level, right? So we need to at least be able to, model things like natural numbers, right? So it's not directly possible in Scala, as you know. You can't say you can have type depend on number 100. So you just can't do that. So you need some kind of encoding where you represent something that looks like natural number or at type level. So there's one very common encoding, sometimes called church encoding. So natural number is either 0 or successor of any other number. So this we can very easily model in Scala. As you can see here, we just use a type member that carries the structure of our number, or type level representation of number. We use subtyping to model, the cases, so to say, the recursion here. And yes, in this way we can obtain singleton types, meaning types that have only one instance possible that model our natural numbers, like 0, 1, 2, 3. So here are the types that denote the numbers, the corresponding numbers, and these values here are the only instances of this type representing numbers 0, 1, 2, 3, and so on, so on. But would we be able to work with seamlessly with integers, with integer literals, and convert them? Well, and there's where it starts to get problematic. So, for instance, you can write macro to achieve this. This macro would basically take the number and apply successor type as many times as needed to obtain its type level representation. But that would work only for literals, for constants. Because if you're given just I, variable I, then you would not know how many times to apply the type constructor. So it works only for literals. In .t, I heard it might be easier to write this case with the advent of so-called transparent functions. It would make it maybe more natural to write, but still, these functions would work only for constants. You can think you can fool the system and write a simple recursive function that will take an integer number and represent it as and return a natural number. Well, in theory, yes, you can write it like this, but then the only thing you can return from this function, or declare to return from this function, is a generic natural number. This is what I mean when I say no type preservation. The compiler just knows. The compiler just knows that you're returning natural number. It doesn't know its structure. This is going to be very important later on. I'll go back to this slide. But for now, remember that you can't just write it in this manner. There's no type preservation. Nothing would work if you write it like this. Not that it would buy you much, because still you cannot. For instance, you would like to be able to say that tail function only works for non-empty vectors. But still, you cannot pattern match on type level in Scala, so that wouldn't buy you that much. So, okay, we need to constrain ourselves a bit only to constants. But if we do that, then we can form more elaborate types. For instance, this is a type of finitely bounded integers, meaning integers in some range. The idea here is that we have a type that's dependent on natural number, and we limit recursion in this type constructor. Yes, we can do this. We can just encode it using the encoding of natural numbers we devised earlier. We can simply model this case, this type level recursion here, using type parameters with appropriate constraints. And but it's useless if you cannot do any computation on this, right? So, can we write a function that converts between these two representations? On type level, meaning at compile time. Now, yes, and this is almost algorithmic. This is almost algorithmic process. So you just take any function like this. You need to encode it as a type. So, well, just create a type out of this function. You take its arguments. You encode arguments as type parameters. You encode result as a type member. You use something called aux pattern, but I don't really like the name. Because this type basically denotes that the result of fin to nat computation for some argument f is n, which is a subtype of natural number. The idea here is that you need to capture the result here, right? In type variable where you want the structure to be preserved. And then, how will you encode recursion, basically? The question is. So you need to be able to influence some computation that's done by compiler. Compiler does a lot of computation. For instance, unifies types, computes upper, lower type bounds, and so on, but all these are set in stone. You cannot influence them in any manner. But there is one thing, well, unique to Scala, I'd say, that you can influence. That's implicit search, and it happens during compile time. So the only way to do it is to encode it as a recursive implicit search. You take basically base case, which is that for 0, the first element of a range is 0. You are able to form, to write the correct implicit for this case. You state that result for 0th element is 0, and you are able to create the instance right away of this type. And then basically you take a recursive case and you encode it as a recursive implicit search. So you say that, yes, I'm able to compute it for successor of any number. If I'm able to do it for number 1 less, and the result of doing it for number 1 less is so far, then the result for number 1 more, for successor of this number, will be successor of what has been found earlier. And with help, yes, and you can write the correct incidence, thus proving that this that you can finish this computation, so to say, and yeah, it basically works. There is one more trick, maybe not unique to Scala, but which you need to do. You can't just return a natural number here, because you lose this type preservation we were talking about earlier. You need to return very precise type, the exact type that has been found during this search. So you need to use a dependent method in Scala. To preserve the structure. So you don't just return a nut, you're returning a successor of, for instance, a 0. So that compiler knows the exact structure, because it will be used in recursive implicit searches later on to derive properties you want to be derived. You can take more or less arbitrary complex recursive functions like this and just algorithmically apply this technique, so to say, and does encoding more and more complex computations. Everything by applying Elg's pattern and recursive implicit search. Sometimes it's even better than Idris, because Idris needs to represent a general case where you pass arbitrary integer. So, for instance, a conversion from finitely bounded natural number to finitely bounded natural number might not work. If I ask you to, convert a number 6 to a range 0 to 2, it's not possible. So in Idris, you need to represent this case as kind of an option type. Whereas in Scala, it's not needed, because the nature of implicit search is such that if such conversion cannot be performed, then the program won't compile anyway. So the only possible conversions arise from programs that can't be compiled, so we don't need to be bothered by any option. But you lose the ability to represent general variables. That's what you get when you restrict, or when you are restricted to only constants, basically. All right, so given all this, we can write a poster child of dependent typing, meaning dependently typed collection in Scala. Sometimes you need to be a bit creative, because, for instance, the tail and head functions, which you want only to work for non-empty vectors, well, you would be inclined to write a pattern match like this, but this won't compile. The pattern match doesn't work with. You can pattern match and generate types like this. Oops, sorry. So you need to have some evidence of. You need to basically recreate a pattern match on type level. So you need to be a bit more creative. So you just, the property you want to pattern match on, you just create it as a type. You capture the types you want. You create kind of unapply methods you like. You want to extract from what you captured. And again, repeating the same process over and over again. You just demand this. You just fire basically this implicit search, and it gives you all you need. So yes, you can write cases like this, which gives you the same thing you do in Idris, right? In Idris, you can create a vector of 2 elements, and you can do, say, tail, tail, tail on this. That's a compilation error. And in Scala, yes, you can recreate the same functionality. I create a vector of 2 elements, and I cannot just go too far into this vector. Maybe the error messages are nicer here, but probably that's something you can work around with something like like implicit not found annotations or so on, so on. All right, so that's good, right? Is it? Well, you might be concerned that this is kind of a cheating because all the collections I was presenting were of known length, statically known length, which is not really the case for the collections, right? The collections usually come from, I don't know, JSON deserialization or database, and there the length is unknown. If you think of it, that becomes a bit of a problem, because if length is part of a type, and the length is unknown, then how would you represent this type? Is it even possible? Well, in dependent type theory, there is a device for this called sigma type, which is not really maybe the most expressive name. Sometimes known as dependent pair. That's a better name for this purpose. More or less, it says that, for instance, if your vector comes from internet or database, you don't represent the type of this vector as vector. You represent it as a different type. And the type checker in Idris won't allow you, there's not much you can do with this type. Almost nothing. But the idea here is that the first, this is a pair basically, the first element of this pair keeps length, the runtime length, and the second argument of this pair has a type that's dependent on whatever is in the first part. Which means that I cannot do much with this type, almost nothing, but I can create assertions about its first part, and then the type of the second part will follow, so to say. So once I check that the first argument is 0, then I know that the type of the second argument is empty vector. If I say assert that it's non-empty, then I can do whatever I can with non-empty vector. But so it's not that independent type system type checker magically knows what size of a collection is. It just won't allow you to do anything with it unless you assert something about their length. So it forces you to do these assertions. How can we do that in Scala? Well, it's not a problem that the sigma type dependent pair cannot be represented in Scala. It can be represented just fine. So I can create a dependent pair in Scala, and if I put as a first argument our type level 2, then the second argument can only be a vector of length 2. If not, it won't compile, and so on, so on. So this is not a problem. The problem is basically this slide. Yes, you can have arbitrary number there, but then you will lose track of what the structure of this number is, and you won't be able to recreate it. Very fast experiment here using some reflection magic. If I get the type level, our type level 2, our type level singleton type 2, then it is known that it's a successor of 1, and all this implicit search machinery works. But if I lose this singleton type, for instance, and it doesn't take much to lose it, for instance, I just cast it up, so to say, to a generic natural number, then nothing works. Because the structure of this number, which is needed in all this implicit machinery, is lost forever, basically. So this is kind of a bridge you can't cross. If you ever lose this singleton type, then compiler won't be able to keep track of what you're trying to do. Which means that all the examples, all the functionalities or features of collections, like filter, cannot be really represented in Scala, because after filtering you won't know what the size of the collection will be. In dependently typed language, you would return you would declare that filter returns a dependent pair type, right? Also, you can express only, so yeah, because of this, you can express only statically, collections of size that are statically known, which is not really the case for the collections, right? So this is not really practical, I would say. Filter doesn't work, and collections of unknown length doesn't work. So is it worth pursuing this dependent type dream in Scala? Well, there are cases where it's okay, like a printf case, which I was mentioning earlier. So the printf is as value dependent thing as you'll see in your life. It's as value dependent as it gets. The printf, the format string to print function is seamlessly lifted to a type, in a way that a printf of this format string has a correct type, string to int to string, whereas printf of this format string has a string to double to string. Can you do that in Scala? Well, there is some bridge you can cross, as I showed earlier. Meaning you can't just seamlessly go from a string to a type, right? You can work around this using macro or transparent functions if they are implemented in .t, but then you would be still restricted basically to constants. But in printf case, it doesn't hurt you that much. Even though you can't have a variable string format, no one would cry, right? Because usually you want to have only constant string formats to print. So in this case, yes, you can recreate these using the same techniques we were talking about before. And yes, you can have a very precise type of printf. If you pass a literal equals number, you have string to into string. If you pass a literal equals double, it's string to doubles to string. So the type can be as precise as you want. And you won't cry over lost functionality of not being able to represent variable format strings, right? So this is the case that looks practical. And I guess the takeaway is that yes, you are limited in what you can represent in Scala. You're basically limited to things that are known at compile time because of the nature how we encode it. Meaning we encode it as as we need to preserve structures. We need to encode exact structure, and we cannot make compiler assert or recreate the structure from runtime variable. We don't have this ability in Scala. But there are cases where it's okay. The cases like state machines, the cases like sprintf here, where everything is known at compile time, then yes, you can enjoy the benefits of having a really precise type following the argument you pass to it. In other cases, it's not that much practical, and probably you don't want to be bothered with it. And I guess that's it. Thank you. Thank you. Mille grazie. Is it how you say it? Thank you very much.
Is it on? Okay. I think we have a couple of questions we can accept. We have time for a couple. If you have any questions. I see puzzled faces here.
No, everything was just obvious, I mean.
Yeah, probably they got everything.
Oh. Sorry, I don't have time for
So, not a question. If there are any questions, just pipe up. Otherwise, I'm going to make a comment. So, you say that there's sort of an unbridgeable divide when dealing with, say runtime properties. But
yes, I think so.
It's not quite so clear, because what you demonstrated was that if your dependent pair contains a representation of the length and the value, then yes, you're absolutely right. Given that, it's not possible to do then at runtime subsequently do the implicit resolution, which is giving you your type
Right,
level
because
pattern
the
match.
structure is lost
Yeah,
forever. It
that's
can't
right.
be created.
But prior to that, the point at which you constructed your dependent pair, wherever you did that, you had all the relevant knowledge. So what you could do at that point, and in the case of length, it's not particularly interesting or useful, but in more general cases, maybe it is. Actually, you just compute the witness at that point, and you pack that into your dependent pair.
Right. If you are able to do this, then
If you're and clearly in the case of length, it's not going to be useful
Right.
because I will have pre-computed a witness for the length of this particular list. Well, I might as well just give you the value in that case. But there are going to be
Right.
more interesting cases where you might be able to usefully compute some set of witnesses which are effectively providing you with runtime surrogates for whatever
Right.
compile time match or type level matching you would have actually done.
right, that's much better said. I agree with it completely. Okay, so sometimes maybe it's not that the world is divided between constants and variables. It's divided into things that you can compute some kind of witness, some kind of structure that you can then work over with implicit search and so on, and not. I'm not sure that if I said that clearly. So it's not about constants and not constants, and constants are variables. It's about things you can effectively search for some kind of witness at compile time and not. All right. Thank you very much for this comment.
Last question.
Do you have an example of such a case off the top of your head? Maybe that would be easier. Yeah. I couldn't figure it out either. Maybe it would be easier to show. But right, I agree totally.
Okay. Thank you, Marcin. Thank you, everybody.